The last couple of days we've been talking about relations. All right. On the first day we talked about how there's different types of relations in math. Yesterday we started talking about functions and how that's a special sort of relationship where every x number or every input is paired with only one output. Okay. So before we go on and talk about discrete and continuous functions and relations, I just want to quickly go over what it is that we talked about yesterday. So again, a function is a relationship where every x is paired up with only one y. Okay, every input has one output. Every independent variable has only one dependent variable it goes with. Okay. A reminder that these words right here, input, x, independent variable, domain, they all mean the same thing and they're interchangeable. If I'm talking about the input, I'm also talking about the domain. If I'm talking about the x number, I'm talking about the independent variable. Same thing with the output. Output, y, dependent variable, range, all of those mean the exact same thing and can be interchanged. So I could be talking in a problem about the input, means I'm talking about the x, and I want you to tell me what the range is. That means I want you to tell me what the y numbers or the answer is. And those things can go back and forth. So today, we're going to talk about discrete and continuous functions and relations. Okay. So first, let's start off with a couple of definitions. Discrete. Discrete means that there's a certain number of possible values in a situation. An example of that would be like, how many kids are in this classroom right now? Okay, there could be, you could have 0 kids. That's the fewest you could have. The most we could probably fit in here would be like 40 kids. So there's only certain numbers in this situation, how many kids can fit in this classroom, that would be possible answers, making this a discrete situation. Okay, it doesn't matter which number you pick, there's only a certain amount of answers that are possible. Whenever you see a table or a mapping or a set of ordered pairs, these are always discrete situations. Okay, those are the only answers that apply to that particular problem. So you can't do anything, you can't get any more answers, you can't find any more inputs or outputs except for the ones that are given to you in the table, the mapping, or the set of ordered pairs. For continuous, a continuous relationship or function has an endless number of possibilities. Okay? And we're going to find this in equations. So if we start with a simple equation that like we've used before, like y equals x, well, x could be any number in the world. X could be 1, or it could be 1.1, or it could be 1.11, or it could be 1.000000006. All right? There's billions and billions of different numbers that x could be, which would give us an answer. So that makes the situation continuous, where there's not a certain amount of possible outcomes that could happen. Let's take a look at some examples. Well, before we do that, I just want to go over one more time that tables, mappings, and sets of ordered pairs are always going to be discrete situations. Okay, whenever you see that, there's just a certain number of x's and a certain number of y's in those problems. Whenever you have an equation, it's always going to be continuous, because you can plug any number in for x. It doesn't matter how small the decimal or what kind of fraction it is or anything, so there's billions and billions of different answers. Where you might have some trouble is when we get to graphs and word problems, because graphs and word problems can be both discrete or continuous. So let's look at an example of a graph. So here is an example of a discrete graph. Okay. On this graph, all we have are dots. Each one of these dots goes with a certain number. Okay, let's just pretend that this dot right here goes down, and this is where x is 2, and maybe this is where y is 3. Okay, this dot is probably touching at 3 for x, this one's probably at 4, we'll say this one's at 5. These, and then we have -1, both of these are on -3, and we'll say that one's a -6. These are the only x values in this problem that would work. I can't say that -7 would be on this graph, or +1, or even 0, because there's no dots that go with it. So this is a discrete graph where there's only a certain number of values that go with x or y. Okay. Another type of graph that we will see is a continuous graph. A continuous graph will look something like this, where we have a line. It could be a closed shape, it could be a rectangle or a circle or any sort of line where they're connected together, where a bunch of points are connected together. Okay, because I can't just say that there's just whole numbers. So here's where x is 1 and x is 2. I'm going to zoom in so you can see that better. So right here, x is 1 and x is 2, and they both touch the graph. But there's all these different points in between. Okay? There's 1.1 and 1.2 and 1.3 and 1.4 and 1.5, and even in between those points would be more points. In between 1.1 and 1.2 could be 1.15 and 1.16 and 1.17 and 1.18. Okay? So there's billions and billions of different answers that if I was able to zoom in close enough, you could see all these different points on the graph. So that's what makes it continuous, that there's an endless number of possible answers. There's not just a certain number like there was with the graph with the points. So again, with the graphs, we have discrete, where it's just the points. And then we have continuous, where it's a line that is connected somehow. It could be a line, a curve, some sort of solid shape. As long as there's a line drawn on the graph and points are connected, it's continuous. Now, the last type of problems we're going to talk about are word problems. So we'll start with an example of a discrete situation or a discrete word problem. So basketballs cost $12 each. I want you to think, using the definition that we already talked about, discrete, only having a certain number of possible values, why that situation would be considered discrete. I'm going to give you guys a few seconds to think about that. So, why do you guys think that buying basketballs that cost $12 each would be a discrete situation? Anybody have any ideas? Okay, so this is a discrete situation because you can only buy whole numbers of basketballs, all right? I can't buy an endless amount of basketballs. I can start with 0, and then I can buy 1 ball, or I can buy 2 balls, or I can buy 3 balls, or I can buy 4 balls, or I can buy all the balls until they're all out of the store, okay? And then how much money I'm gonna pay? Well, if I buy 0, I'm gonna pay $0. If I buy 1, I'm gonna pay $12. If I buy 2, I'm gonna pay $24. So there's no way, there's no situation where I'm gonna pay $15. Or I'm going to pay just $3. Okay, there's only certain numbers that apply to this particular situation that makes it discrete. Unlike our example on the bottom of a continuous word problem, which is the amount of water in a glass. So I could have a glass of water. Let's say maybe the glass holds 16 ounces and I fill it all the way to the top. So I have 16 ounces of water. But then I take a sip of water. Maybe I just have 15 ounces left. Or maybe I have 15.1. Or maybe I have 14.9. It depends on how much I drank. I could have anywhere in between that. I could have 15, or I could have 14.9368 ounces of water left. And then the water sits there for a while, so maybe some of the water evaporates, and now I'm down to 14.876 ounces of water. So an amount of water where I can have millions and millions of different possibilities is going to be an example of a continuous situation.